Okay, good afternoon, folks. Okay, we don't have a lot of stuff left to cover, just a few slides, and that shouldn't take that long. And then I will go through some sample problems. I won't finish it today because of two reasons. Number one is the fact that we still have a lecture next week, and the lecture will also have the last quiz. So, there should be some incentive for you to come other than just a quiz, right? Quiz is a compulsion, not an incentive, right? And second reason is that my throat is out of order. So I'm not sure if I can talk for that long either. Okay, so yeah, let's get started. But before we go into the rest of the stuff left in this chapter, let me just clarify a couple of things. One is, one question I got is, why is there an address connection to here, whereas there is no address connection here or here? What is the reason? In fact, this is exactly the case with your wrapper as well. Remember, I had mentioned that whatever you see here is exactly how it is implemented in the wrapper. Okay, even though you did not write the wrapper yourself, please do go through the wrapper so that you can understand better how all these things are managed. So when the address is issued by the processor, the address is nothing but ALU result, because ALU is the one which computes the address, right? So when the address is sent over, the address decoder looks at the address. Okay, you can see it in your wrapper quite easily that there is this part where the various address ranges are compared. Okay, and depending on the specific address range, the specific device is enabled. So, for example, let's assume that memory has an address of, let's say, 400, or in your case, actually it is 200 to 3FF, if I recall correctly. So if the address falls within that range, then the address decoder will enable the memory. And let's consider for now a write operation. Okay, so the write enable is enabled provided the address end is in this range and memwrite is asserted. Because without memwrite, the instruction is essentially not writing to the memory, right? So if the address falls within the range and if memwrite is asserted, then the write enable for the memory is asserted. And the memory itself will require the address. Just because the write address is not write enable is asserted does not mean the memory knows where exactly to write. Write enable is just a consent or a prompt to write. You still need to know the address within the device, the address sort of local to the device, to decide where exactly within the memory it should be put in, right? And that is typically the last few bits. So when you have a big range or a big address, let's say a 32-bit address, okay, something like say ABCD, 1, 2, 3, 4. The first few bits are typically used, or bytes, or first a certain number of bytes are used for decoding. That is to figure out which device is being addressed. So for example, if you are looking at a device with let's say 2 raised to 16 locations, okay, then to identify that it is a device, the first 16 bits will be used. And to identify the locations within the device, you will be using the last 16 bits. So the last 16 bits is essentially the address that is local to the device. And the first few bits, that is in this case, let's say 16 bits, will be used to identify the device itself. So in order to identify the specific location within the device, you will require the address. But then why don't we do it for other devices? It may or may not be required for other devices depending on what is the nature of the device. So let's say if you are looking at a device which has a large number of so-called registers within it, These registers are peripheral registers which are treated just like memory. So in order to identify which peripheral register within that device we are addressing, we still require a few bits. Okay, so the address line, usually some lower order few bits of the address line has to be connected to the device. Whereas for some other devices, it may not be required. Can you give an example for a device which we write, which doesn't require any further addressing within the device? An example for a device that we write, but there is no further addressing within the device, local to the device, that we have in our lab. Yes, excellent, LED, right? It's just one single address location. You write to that address location, in your case, if you are using ARM, I believe it was C00, right? So if you write to that address, you are essentially writing to the LED. There is no further addressing required or even possible within that. All the LED can do is to accept 32 bits of data, right? Or less, depending on the number of bits available within the LED. But yeah, assume 32 bits of data. That's all. So imagine this is an LED type device. So it can accept just 32 bits of data. So it has one single address, and when that address is sent, the write enable for that device will be enabled, and the device will capture the data. And typically for some simple devices like LED, you will have something to store or latch the data in, right? So that's why you will have a register. And even if you look into the wrapper, you can see there is actually a register implemented within the wrapper which actually holds the data which is to be displayed on LEDs. LEDs themselves can't really hold any data, it doesn't have memory, right? So it typically requires a flip-flop to feed it, and that's why you have this flip-flop. But of course this can't be LED because this was an output too, and LED is basically just an output device which accepts an input, but it doesn't give an output back to the system, right? I mean, from the processor's perspective, it's a device that the processor writes to. It doesn't read from that device. Whereas your switch is the other way around. You don't write to the device, but you will read from the device. And here, in order to decide which device is being read, there is some sort of a decoding or selection here. And this is done when the operation is read. So the device that is being activated will be the one which is selected by the multiplexer, and that also depends on the selection signal that is sent by the address decoder. So the address decoder will check which device it corresponds to, and the corresponding device will be activated or will be selected by the multiplexer. Again, very similar to how it is done in wrapper. Okay, you look at the range of address and then enable the selection of that device. And devices will be selected in a mutually exclusive manner, so eventually only one device's output will become the input to the processor. That's the idea. Okay, so that's that. Another mistake I made in the last class is that when I was talking about this, I mentioned that R14 is a Kodi safe register. In fact, I stand corrected. R14 is neither Kodi safe nor caller safe. It's unfair to call it or categorize it to either of the two. R14 is simply a special register. Okay, in reality, both the parties need to save it. So let's say if I have a main function from which I am calling another function, right? So in assembly language, the equivalent of this will be, okay, a certain main subroutine or code, and you will do some BL function. And within the function, you will have a bunch of stuff, and finally you will have some BX, LR or R14. So any R14 value that is required later, at this point, will have to be saved before you call the BL. Because the moment you call BL, link register is updated. So any content that is already there in the link register is overwritten. So if that content is important to you, before BL, the caller function should save it, right? And then it goes to the callee function. And within the callee function, there is always a possibility that it calls another function. So before that function call, the callee function, which now becomes the caller, also has to save it. So in that sense, both parties actually have to save it. So it's not like your registers R0 to R3 where it's entirely the responsibility of the caller, and R4 to R11 is entirely the responsibility of callee, right? Whereas for R14, that kind of a split is not quite possible. So since both parties sort of have to save it, for an interrupt service routine, since it's like a function call made by the hardware, the caller is in some sense the hardware, so the caller has to save LR as well. Okay, otherwise, any value that is stored within LR will be overwritten when the interrupt service routine is invoked. So yeah. By the way, R12 is also a caller saved register, and that's why hardware saves R12 as well. So R0 to R3 and R12 are caller saved. Okay, R4 to R11 are callee saved. The rest of the registers, R13, 14 and 15 are special registers where you can't really categorize it that easily. Now R12 is also used for a certain reason by linker for function calls which are very far away from the current instruction. You can read up more about it if you are interested. Okay, so it's a scratch pad register that is used by the linker. Okay, now back to what we were discussing in the last class. So we had seen programmed input output. We had seen the alternative, which is DMA. Programmed input output is repeated LDR, STR to move data from let's say location or device A to a location or device B. Whereas DMA is a more efficient mechanism whereby the movement of data is handled by a special controller or an assistant. So the processor just needs to command to the helper, the DMA controller, that this much amount of data is to be moved from say location A to a location B. And then the DMA controller will do that moving, and eventually when the requested data has been successfully moved, it will let the processor know by generating an interrupt. So the processor doesn't need to be involved in moving data byte by byte or word by word. Okay, now we had also seen parallel versus serial protocols. This is where we were towards the end of the last lecture, where parallel protocols are used for very short distance, very high speed communications, like processor to memory buses or communication within a chip are typically parallel. Okay, the distances you are looking at are in the range of millimeters or lower centimeter range. And then parallel protocols are pretty good, and you can get several tens of gigabytes per second bandwidth. Whereas when the data is sent off chip, typically parallel protocols are not used. Okay, it can be still used within a board, like for example, your processor communicates with your memory, and memory is, especially for desktop systems, a totally separate chip altogether. So the data will travel off chip, that is between chips. But still, these are physically close to each other, so the distance between the two is not so high. Okay, but if the distance exceeds say a few centimeters, so if it gets into the range of tens of centimeters, we typically do not use parallel protocols. We saw the reason for that even if you are sending it all together at the transmitter side, at the receiver side, there could be differences at which, or differences in the times at which the various bits reach. Okay, which is influenced by a number of factors such as the length of the wire, which might not be exactly the same for the different wires which carry the same word. Yeah. So the different wires which carry different bits of the same word. So they may not be the same, and then these wires that carry individual bits might be affected differently by inductance, capacitance, resistance, etc., which can all influence the propagation of signals through the wire. So you could end up in a situation where some bits arrive at some time, some other bits arrive at some other time. And then the window of time for which all the bits correspond with each other, that is all the bits corresponding to a byte or a word are all available at the same time, might be a narrow window. For example, here you are sending 110 and here it is 110 only for a narrow window. So if you are sampling outside that window, your sample data is wrong. And to maximize the probability of sampling it correctly, you have to maximize this window. And pretty much the only way to maximize that window is to make sure that each bit is long enough. And if each bit is long enough, your bit transmission rate is going down, which essentially means your communication speed is going down. And that was supposedly the main or the only advantage of parallel protocols in a way, right? And that backfires in such a case. And there are also other issues such as crosstalk, where wires affect each other. Now, some of you were asking this question towards the end of the lecture. So why don't we just wait until all the bits for a byte arrive before you sample it? Well, it's not possible because we don't know. We don't know whether a particular bit corresponds to a certain byte or the previous byte. Each bit does not come with a tag which shows which byte it belongs to, right? Each byte does not have a sort of a tag or a sequence number for us to know whether it belongs to this byte or the previous byte, or to identify whether a bit corresponds to a certain byte or a previous byte. That's not possible. Okay, so the only way is to make sure that this window is longer, which inevitably affects the transmission speed. Okay, and another obvious disadvantage of parallel protocols, which is too obvious that I did not list it, is anyone? Yeah, cost. Like number of wires required is higher. Okay, and for modern day chips, the number of wires that comes out of a chip affects the production cost very significantly. And it's not just the production cost of the chip itself. Eventually the chip will be soldered onto some kind of a board, right? A printed circuit board. And the board will require more tracks to connect it to another chip. And whenever you send something from one chip to another chip, you have to send it using typically high current, because there is a very significant capacitance to overcome, right? If you are using large connectors which are required to route it through the motherboard or a printed circuit board, you need to drive it at a pretty high current. Okay, and that current is, especially in this age and time, a very, very significant contributor to the system power consumption. Okay, in fact, in many cases, especially in embedded systems, if your memory is separate from the processor, the current or the energy required to send the data from processor to memory could be higher than the power consumed by the processor itself or the memory itself. Okay, so yeah, so number of wires do have a lot of implications. So that's another disadvantage, obviously, and that's where asynchronous serial protocols come into play, where the different bits within a byte are sent over the same wire one after the other, right? So what if your transmission rate has to be higher? Then these days what we do is to have multiple independent serial links rather than sending data in parallel. And that is exactly how technology such as PCI Express works. If you have bought graphics cards, you will know that you go for a certain PCI slot, right? Like PCI Express or PCI X8, X16, etc. Like higher end graphics cards typically use X16. This means that there are 16 independent lanes, 16 serial lanes. Okay, so one byte or one word is actually transmitted through the same wire. But there could be multiple bytes that are being transmitted through the different wires in parallel. Of course, with the disadvantage that you have issues like crosstalk, but at least skew is not an issue. Because you don't have to maintain correspondence between the various bits on various wires, because they carry separate bytes anyway. Okay, so at least this problem is solved, but this problem still exists, of course. There are various ways to mitigate this, such as sending the data in both its original form and complemented form, and then finding the difference at the end, etc., etc., which is used by many protocols. Like for example, the data is sent like this and sent like this, and then you find the difference, and things which affect, noise which affects both of the wires equally tend to get cancelled out. So yeah, that's the idea of serial versus parallel. The next classification is between synchronous and asynchronous. In synchronous protocols, one of the wires carry a clock. The transmitter and receiver have a common time reference. So there's a common clock. So you look at the clock and decide when to make sense of data. The clock could be generated by one of the party and sent to the other party, or it could be just the clock that is derived from a common source. Okay? So in either case, it is still considered synchronous as long as both parties use a common clock, which is sent by one party or which is generated by a common source. For example, in protocols such as I2C, the clock is generated by one of the devices. Okay, whereas in some other protocols, like for example AXI and many other protocols, it's just a common source that generates clocks for both the devices. It is faster and arguably simpler. The circuitry is arguably simpler because you can simply look at the clock and decide when to make sense of data. For example, if the protocol specifies that you have to look at the positive edges of the clock, you look at every positive edge of the clock and sample the data. Okay, so at the receiver side, all you need is in some sense just a register. There isn't a need for much complicated circuitry to receive data. Yep. Now, synchronous protocols can be both parallel and serial. For example, I2C is a serial protocol, whereas AXI or many other internal bus protocols, they are parallel protocols. Okay, but they both have the same characteristic, that is they are synchronous. That is, there is a shared clock between the transmitter and the receiver. But of course, they do get affected by similar issues as parallel protocols, because in some sense the clock and the data themselves are in parallel, even if the data is sent serially. Right? So the wires could affect each other. Your clock could be received at the receiver at a time which is skewed from the data. So the correspondence may not be maintained, especially if you transmit them over long distances. And then your clock will be more harmful than useful. And I'm not sure if I ask you this question, which is better? Having a watch which might tell you the wrong time, or not having a watch? You are probably better off not having a watch, right? At least you will not be misguided. Yeah. So same thing here. So if you send data over long distances, you typically do not use synchronous protocols. So in most cases, you are limited to centimeters, millimeters, centimeters, or lower tens of centimeters. Okay, usually not much beyond that. Now, the alternative is of course synchronous. Sorry, asynchronous. In asynchronous, only data is transmitted, not clock. So let's say if device 1 sends information to device 2, device 1 can just send the information directly. But then the receiver needs to have some mechanism to make sense of when to make sense of data, or to figure out when to make sense of data. Because just by looking at the data, it might not be that easy to figure out when to sample it, right? So, but of course, techniques do exist whereby you can just look at the data and figure out when to sample. Okay, one simple synchronization technique that is used in protocols such as UART is to look for a guaranteed transition at the beginning of every byte. UART is a very popular protocol. In fact, you could have used it in your lab as your console. Now, when we mention about console, it's actually a UART console. The underlying hardware is simply UART, okay, which transmits data in an asynchronous manner. You just transmit data without any clock. But you typically need some kind of additional bits for some form of synchronization. For example, in UART, when there is no transmission at all, the data line remains high. And before you can transmit a byte, you need to transmit something called a start bit, which is by default a low signal. So the default condition of the line is high, whereas the start bit is a logic low, which means that there is a guaranteed transition at the point when you send the start bit. A high to low transition is guaranteed. So if the receiver circuitry is capable of detecting this transition, and provided it knows how long a bit period is, it knows when to sample. Now the question is, how do we know how long a bit period is? Well, that is a setting that has to be set identically on both devices. So if there is a device 1 and device 2, both the devices should have the same setting with respect to how long a bit period is. But the receiving party does not know when exactly that bit period starts. Okay, it's almost like, let's say, me telling you, there is a surprise quiz next week in the middle of the lecture, but the lecture can be any time. Okay, not necessarily at 6 p.m. on Wednesday. So the only way for you to know is keep checking whether the lecture has started. Once you realize when the lecture has started, you know when the quiz will start. Because you know the duration of a lecture is 2 hours, and you know the quiz will be started exactly in the middle. So if, let's say, the lecture started at, let's say, 11 a.m. on Thursday, then you know that the quiz will be at 12 noon on Thursday, right? So same thing here, you have to repeatedly check for the beginning of the start bit. Once you recognize this transition, that's the beginning of the start bit, and then you know when to sample. And that time reference can be used for the current byte. After the current byte, the line goes back to high and remains high until the start bit of the next byte. But there is a guaranteed transition for the next byte too, because the next byte will be preceded by a start bit. Got the idea? So this is one synchronization mechanism, or one mechanism whereby the receiving party can make sense of the data that is coming in without having a clock that is shared with the transmitting party. But this is just one synchronization mechanism. There are other mechanisms that exist too. Like for example, it could be a handshaking mechanism whereby this device will give a violet signal after putting some data on the bus. So let's say if it put a new bit or byte on the bus, then it will send a violet bit or assert the violet signal. And when this device sees that the violet signal is asserted, it will capture the data and then it will activate a signal called something like acknowledge. And once this device sees that acknowledge is activated, it will change the data here and will assert violet again. Okay, so this device will capture it again and then send an acknowledge. So this is another mechanism. It's a handshaking mechanism whereby data can be sent without having a shared clock. Okay, and there are other additional mechanisms, like for example USB. Okay, a lot of people don't really consider USB as asynchronous, even though going by the definition of the transmitter and the receiver using a shared clock, it is asynchronous. USB does not use a separate clock wire. So if you cut open your USB cable, if it is USB 2.0, there are only 4 connections in fact. One is +5, the other one is ground. The other two carry the exact same signal but in opposite polarity. So both are data wires, one is called D+, the other one is called D-. So there is no clock wire. So the receiver looks at the data and synchronizes its own clock. And then the reception, once it is synchronized, happens sort of synchronously. So the receiver has a clock that is adjusted to be in synchronization with the transmitter. So the clock is not explicitly shared, but it is adjusted by the receiving party. Okay, and that typically requires some kind of a mechanism like phase lock loop. And this also requires that the data has frequent transitions. So if you send a continuous stream of zeros, it doesn't really work, because a receiver cannot really synchronize or make sure that its internal clock is synchronized. So protocols such as USB have mechanisms whereby a transition is guaranteed once every few bits by special encoding schemes. Okay, anyway, if you are interested, you can read up, but some of you might have actually learned some of it in your networks module, right? Then the next one is bus-based versus point-to-point protocols. In a bus-based protocol, a number of devices are connected to the same set of wires. And wire is a bit of a simplification. It could be wires plus some additional circuitry that manages access to the wires, etc. But in any case, when you have a bus-based protocol, every device that is connected to the bus needs to have a unique address, so that when some information is sent, it will be clear who is the intended recipient. Right? Otherwise, there's a confusion. Like, if let's say multiple parties are connected to the bus, who does it belong to? The data that is sent. That is typically recognized using some kind of an address. So every device has a unique address. And depending on the protocol, this address may be hard-coded, which is actually the case for a majority of the protocols. The addresses are typically hard-coded, set in hardware. Or it could be dynamically given, okay, which is the case for some protocols such as USB. In protocols such as I2C and in many other protocols, it's hardwired. So when you buy the device, you already have the address. Or when you design the system, the address for a device is fixed. It cannot be changed, okay, unless you manipulate the hardware. Whereas in some other protocols such as USB, every time you plug in a new device, the device is given an address dynamically. And that's why you are able to connect identical USB devices to the same USB hub. Right? You might have a thumb drive, two thumb drives, or two USB drives which are identical. Right? And if you buy it from China, even the serial numbers, etc., will be identical. And then when you plug it in, the hardware is still able to discriminate between them because the address is dynamically allocated. And when I meant if you buy it from China, I'm talking about buying it from non-branded manufacturers like AliExpress. I do a lot of it, but yeah, you get the point, right? Okay. Yeah, so anyway, in USB the address is dynamically allocated, but either way, each device has a unique address. That's the point here. Yeah. Now, if let's say it is a master-slave protocol, which actually comes soon enough, it's typically a master device who is in control of everything that is going on the bus. Yeah, and it is a master device that typically decides which slave should be participating in the communication among the multiple so-called slaves present. Okay, whereas in a point-to-point protocol, multiple devices are connected to the same, only two devices are typically connected to the same wire, same set of wires. So when device 1 sends information, it's meant for device 2, and when device 2 sends information, it is meant for device 1. So there's no need for any addressing. There is no ambiguity that needs to be resolved, right? You have an ambiguity only when there are more than two devices involved in communication. Then you need to specify which device you are talking to. Whereas if two parties are talking to each other, you don't have to use the other person's name, because there is no confusion whom you are talking to, right? Whereas if you are in a group discussion or something, and then if you want to talk to a specific person, you need to address that person. Okay, typically using names, right? So something similar here. So there is no need for addressing for point-to-point protocols. One example is UART. Another example that some of you might be familiar with is axis stream. Now the next one is master-slave versus peer-to-peer protocols. In a master-slave protocol, only a device that is designated as a master. And in many protocols, there is typically only one master, but there could be more than one master, in which case there will be some mechanism whereby only one master will be in control at any given time. And it is that master device that is in control at that point in time who can initiate a communication, decides which slave should respond, in other words, generates the address, and in some protocols it also generates the clock. So examples are I2C, SPI, USB, AHB, etc. In fact, vast majority of the protocols out there are master-slave protocols. Okay, and most internal buses of processors, etc. are master-slave, where the processor is typically the master. But sometimes the processor can delegate the master responsibility to other devices, which is typically what happens with DMA. Okay, when there is a DMA transfer, the processor will delegate or pass the responsibility of being the master to the DMA controller. And then it's a DMA controller who is in charge until it has finished communication or until it is sort of interrupted by the processor. Now, these days the term master-slave is considered a bit derogatory. So some of the modern protocols such as USB uses nicer terminology such as host and device. More politically correct. Then there are peer-to-peer protocols where it's a communication between equals. Okay, like in an ideal egalitarian society where everyone is kind of equal. That's peer-to-peer. So any party can initiate communication, but that also comes with the risk that two parties can initiate communication at the same time, and then there will be a collision. So typically the protocol does have a built-in mechanism. The protocol specifies a mechanism whereby the collision can be detected and one or sometimes both of the parties will back off. Like for example, again, you might have heard of how studied how Ethernet works, right? The transmitting party generates a carrier, and if two parties generate the carrier at the same time, then there is a collision, and they will back off and wait for a certain random period of time before trying again, right? So that's one methodology whereby data corruption is prevented. So there are similar such mechanisms in peer-to-peer protocols. Now, depending on the direction of communication, there are three categories of protocols: simplex, half duplex, and full duplex, which is fairly obvious even from the name. Simplex is a single unidirectional link for one-way interaction. Okay, for example, the data always flows from device 1 to device 2 and never really the other way around. It doesn't mean there is only one wire. It could be a parallel link or a serial link, but the link is unidirectional from one device to the other device. For example, the connection between processor and LEDs, the GPIO connection from a processor to LED is practically unidirectional. The processor writes to LEDs, the processor doesn't read from LEDs, right? For switches, it's the other way around. The information flows from a switch to the processor. You don't write to the switch, you only read from the switch, right? Then there is half duplex, whereby there is still only one link, but that link is a bidirectional link. So device 1 can send information to device 2, device 2 can send information to device 1, but not at the same time, not simultaneously. Because there is only one link. It can carry data only in one direction at one point in time. But at some other point in time, it could be in the other direction. That's the idea. So that's half duplex. Examples are I2C, USB 2.0, etc. USB 2 or earlier versions, where there is only one practical data link. Okay, so the information can flow only in one direction at a time, but at different points in time, it can be in different directions. Then we have full duplex. By the way, the newer versions of USB, like USB 3.0 and higher, are full duplex. There are multiple data links between, or multiple data links through the USB cable or USB plug. Okay, so yeah, if you have a USB 3 cable lying around, cut open and see how many wires are there. You will be surprised to see that the number of wires is actually more than what you expect. Okay, but you will get your answer if you look at the USB connector very carefully. You can see deep within it, sort of hidden within it, there are more connectors. Okay, that's where full duplex comes in, where there are at least two links, possibly more, and can transmit and receive data at the same time. So it's entirely possible that you will be transmitting and receiving at the same time. Okay, examples are UART, SPI, USB 3.x, etc. So in a very popular protocol SPI, you will actually be transmitting and receiving at the same time. Okay, same goes for UART in their default implementations. Of course, for both SPI and UART, there are versions which are half duplex or even simplex, but the default implementation of these protocols are as full duplex protocols, where you have one wire for one direction, another wire or link for the other direction. Okay, so that oh no, we haven't done yet. We are not done yet. Yeah, the last point is addressing. In-band versus out-of-band addressing. So in a bus-based protocol, there are multiple devices connected, and each device needs to have a separate address, right? So that the party which initiates a communication, for example, a master, will send that address to specify which device it is talking to. And this address can be sent possibly over the same bus as data, or possibly using a separate bus. So if the address is sent over the same bus as data, then it's called in-band addressing. So the address of the device being accessed as well as the data are sent through the same bus, which is the case for protocols such as USB, I2C, etc., where there are no separate data and address buses. It all passes through the same set of wires. So it's very typical to first send the address. So the master, which is initiating communication, will send the address of the device it wants to talk to. And let's say if the master wants to talk to this device, then the master will send the address of this device. This device will say, okay, I'm here, and then the communication will happen. Okay, until the master terminates the communication and reinitiates another communication. So until that point, that is during a current transfer, it will be just between this party and this party. The other parties have the flexibility to listen to what is going on, but they are not going to be active participants in the communication. Okay, the protocol typically requires that these devices which are not being addressed are practically non-existent on the bus. Whereas in out-of-band addressing, which is typically the case for higher speed protocols, the internal buses within a chip, etc., which are typically out of band, where there is a separate address bus. So the address is sent through a separate address bus, and a decoder enables the device. So there is this decoder which will look at the address and will activate the enable of the appropriate peripheral. Okay, so you could present the data as well as the address of the device at the same time. Okay, you can put in the data to be sent, and you can put in or output the address of the device to be sent at the same time. So there is more parallelism here, which naturally means that you can get higher throughput or higher performance given everything else remains equal, right? Whereas here there is some sequentiality. You have to first send the address and then send the data, and that sequentiality will of course come at the price of performance or data transmission speeds or bandwidth. But advantage here is in-band addressing has an advantage that yeah. You require less number of wires. Okay, and often there is also this advantage of hot pluggability, which means that devices can be added or removed from the bus without turning off the system or without affecting other devices. Like USB, right? You can just plug in a device without affecting others. Whereas if it is an in-band addressing, if it is an out-of-band addressing, it typically requires some hardware connection or arrangement before you can use it. Whereas those with in-band addressing can typically be hot plugged. Now we are truly done. As you might have realized by now, computer architecture is a fast evolving field, and now the modern trend is certainly towards creating custom accelerators which can accelerate certain computations. Especially now that there's a lot of data, everyone talks about data. So there needs to be eventually hardware to crunch all this data, right? So specialized processors which can do certain things more efficiently is a pretty hot topic right now. And please do go through the various tech websites like Tom's Hardware, Anand Tech, or even our own Hardware Zone to be abreast with what's going on in this field. Yeah, things change pretty fast. Every 5 years there is a radically new technology out there, and computers look quite different every 5 years. I mean, not external looks, but how it is internally. Okay, so yeah, that's all. There is this famous statement which I like quite a bit. We cannot really predict the future, but we can invent it. Okay, and that's your job. So yeah, that's all, folks. We are done with the lectures. Now let's not waste much time and go straight into some of the example problems. I will cover maybe 4 or 5 of them, and then we will sort the lecture. Okay, so let's have a behavior which is kind of similar to a stack, which is we are going to deal with the last things first. Okay, most of these are actually taken from past year papers. So the questions that you see here are kind of indicative of the kind of questions you can expect. For this module, past year papers are not released, partly because there is a very significant MCQ component. And for any module with MCQs, it's very challenging to have like totally radically new questions every time. While the questions are not repeated verbatim, some repetition here and there is inevitable. And especially since we are dealing with, a limited instruction set, so the degrees of freedom that I have as an examiner is kind of limited with respect to the kind of questions I can ask. Okay, so that is also partly the reason why the past year papers are not released, but there are some sample problems, there are quiz problems. I will put up even more problems for you to try on your own in Luminous, so not Luminous, Canvas. So yeah, I think those should suffice as practice, but more important is to understand concepts. And once you understand those, well, the rest of it will come naturally. By the way, some of you were asking about exam format. The exam has 22 MCQs, 2 marks each. Okay, 4 choices typically per question. So yeah. Okay, so even if you don't know the answer for a question, it's okay to blind guess, which is better than not guessing at all, because probabilistically you will get something, especially since there is no penalty for wrong answers. There is no negative mark. Yeah. And that leaves us with 56 marks, which is 8 questions of 7 marks each. 8 into 7 marks questions. Which is short to medium answer questions. Okay, and now that we are back to face-to-face exams, there could be questions which might require you to draw things. Okay, so it's a good idea to have pencil and eraser with you. And unlike most other modules, you will be writing the answer on the question paper itself in the space provided to you. No extra sheet will be provided. Okay, so make sure that you limit your answer to your space that is given to you. And final exam is of 2 hours duration, and as you can see here, total of 100 marks, which will be weighed by a factor of 0.4 for your final grades, because it's 40% from final exam. 15 marks from the quizzes and the rest from your marks. GPU is an example for SISD, MISD, SIMD, MIMD. Most hardware accelerators follow SIMD style of processing. Okay. By the way, this is based on Flint's taxonomy, which is kind of an outdated way to categorize computers, because most computers these days are not so categorical that they belong to one of the categories. Okay, so if there is such a question, you have to follow the spirit of the question and choose an option which is the closest. Okay, and the closest is SIMD, even though many modern GPUs can do a fair bit of MIMD kind of processing as well. Now, this is, well, easy enough for you. We already saw it in the lectures. By the way, this was a question from the time when it was closed book. Now that it is open book, it probably won't be a question like this directly, because you can write it straight off the lecture notes. But yeah, for the sake of completeness, let me just go through that part. So, what is the advantage of heterogeneous heterogeneous systems, you get higher performance and lower power consumption for a given application. Okay, the same thing that can be done by a homogeneous system can be done by a heterogeneous system, typically faster for the same hardware or same money that you spend, and at a lower power footprint. Because in a heterogeneous system, you typically have processors which are specialized for certain tasks. While they are not flexible enough to do other tasks, they will do the tasks they can do in a more efficient manner. Okay, as opposed to homogeneous multiprocessor systems where each processor is a jack of all trades, master of none. So it can do everything, but it cannot do anything particularly efficiently. Disadvantages are mainly the difficulty in designing, debugging, evaluating the performance, and scheduling the tasks in such a system. Okay, and there could also be binary incompatibility issues. The binary meant for one processor may not and typically does not run on another processor, especially in cases where ISAs are different. And the failure of one component can bring down the entire system, and it might not even be possible to reprogram the system to even run it at a lower performance. Whereas in a homogeneous multiprocessor system, even if one processor is down, you can possibly change your scheduling such that the entire system uses the other processors. Okay, which might reduce the throughput overall performance, but it's probably better than a complete failure, abrupt failure. And there could also be data format or NDNS issues. The data required for one processor might not be the same for the other, which might require some overheads in formatting the data differently or sequencing the data differently. Like for example, if one processor is big endian, the other one is little endian, you will have to do byte order swap in one of the processors, so that your data meaning will not change when the data returned by one processor is read by the other processor. And there could be other disadvantages which I did not mention about, like there could be requirements to copy the data into from one memory to another memory, etc. Because the two processors might not really share a memory, which is typically the case for GPUs, where you have to copy it over to a certain other memory so that the GPU can process it. A system with DMA systems with DMA do not need interrupts, because DMA is a faster I/O mechanism than interrupts. Well, is it correct? Obviously not, right? DMA and interrupts are typically complementary mechanisms rather than competing mechanisms. Of course, there are situations where interrupts can be used in lieu of DMA, where, for example, if you need to copy some data from one peripheral or one device to, let's say, the RAM, the peripheral might not have the data available all the time. The peripheral could be a slow device, so it might need to buffer a certain amount of data before you can meaningfully copy. So once that much amount of data is buffered, it interrupts the CPU or sends an interrupt to the CPU, and then it can possibly use programmed input-output, that is LDR-STR combination, to copy the data over. Okay, but using a DMA, depending on the DMA capabilities, etc., the DMA controller might actually wait for the data to be available before it copies it over to RAM. The CPU can then just initiate, the DMA controller will do the waiting and copying itself. In which case, yeah, there is some, there's some choice between interrupts and DMA. But by and large, they are not competing mechanisms. they are more of complementary mechanisms, whereby the availability of data is typically made known to the processor using interrupts. So the peripheral will interrupt the processor, and then the processor will initiate a DMA transfer. Okay, sometimes the processor might actually ask the peripheral device, how much data do you have? And then tell the DMA controller, okay, this much is the data to be copied from this device to the ROM. Okay, and then the DMA controller takes over the bus, does the copying, and once it is done with all the copying, it will let the processor know that it is done by raising an interrupt. Okay, so typically DMA is done very much hand in hand with interrupts. The data availability, data copy completion, or any errors, etc., are all communicated to the processor through interrupts. Then the next question is, it's possible to keep increasing the performance by increasing the number of pipeline stages. The number of pipeline stages possible is limited only by the fabrication technology. How true is the above statement? Is fabrication technology having any role at all in the speed of operation of a circuit? Answer is yes. Typically, newer fabrication technologies will produce gates which are faster. Okay, and faster gates would obviously affect the operational speed of the system, because delays, etc., are what limits how fast a circuitry can operate, right? So it's not like fabrication technology has nothing to do with it, but it's not limited just by fabrication technology, right? The main limiting factor is actually the overheads associated with pipelining itself. We saw in the class that the assumption that it's a longest combinational path that limits the maximum frequency of operation is not entirely true. Okay, so there are overheads associated with it, with any data storage or latching of data. For example, if this is a clock period clock that is used to latch or capture the data, this is what we call the launch flip-flop, and this is a capture flip-flop. So it takes a certain amount of time after the clock edge for the data to stabilize at the output of the launch flip-flop. And only then can this circuitry start processing the data meaningfully. So it will take some time for it to process combinationally and to make it available here so that the capture flip-flop can capture it. And it should be made available a certain time before the clock comes to the clock pin of the capture flip-flop. So the data input should be stabilized, or should have stabilized a certain time before the clock. And that's what we call the setup time. The time taken for the data output to stabilize is the propagation delay, or to be precise, clock to Q propagation delay. So the actual time that the combinational circuit in between can take is, if the total time period is T, it is T minus the propagation delay minus setup time. And in reality, there are other overheads. For example, the clock period might not be that constant, so there could be some unpredictability regarding the clock, because after all, no real world system is perfect, right? When you say, let's say the clock period is 10 nanoseconds, it won't be exactly 10 nanoseconds all the time. Sometimes it could be a bit on this side, sometimes it could be a bit on that side. So you have to cater for the worst case scenario where the period available is actually a bit less than the expected period. So you need to have that uncertainty, a certain delta, reduced from the overall available time. Okay, and then there are a few other factors as well, but these are the primary factors. So all these count as overheads. and these overheads eat into the available time within the time period that you have. And these overheads are kind of fixed for a particular fabrication technology, and it's not something that will change with the number of stages of pipeline you have. So just to give you a numeric example, let's say if you have a single cycle processor which requires 1000 picoseconds, and let's assume that the overheads, all these overheads together add up to 100 picoseconds. Then your effective clock period will be 1100 for single cycle. Now if you do a 5-stage pipeline, assuming that you have the ideal scenario where this can be split into 5 equal parts, which is already a very strong assumption. But if it is splittable into 5 equal parts, we have 200 picoseconds per stage. But that's just a combinational delay. You have to add this 100 to each stage because between stages you have the drops, right? So practically the time period becomes 300. So your improvement factor now is 1100 by 300, purely in terms of, or by comparing clock frequencies. Whereas you would have expected 5, you are getting only something just about 3. 3 point something. And this is already assuming that there are no other issues with pipelining at all, there are no hazard issues. But in reality, there are hazard issues. There is time required to fill the pipeline, drain in case of misprediction, stores that may need to be inserted depending on whether certain 2 instructions which don't really like each other are next to each other, and so on and so forth, right? And then of course the imbalance in pipeline stages, which are kind of inevitable, which prevents you from splitting it equally into 5 pieces, etc. So even after considering, or even after not considering all these, you are still getting only 3 point something, even though you have 5-stage pipeline. And now, if let's say you are intending to make a 10-stage pipeline, and assuming that you can split it equally into 10 parts, your clock period now becomes 100 for the combinational part, plus 100, which is overhead. Okay, so your clock period is still 200. So your improvement factor, without considering any other issues with pipelining, is only 5 point something, whereas the ideal value would have been 10, right? And now there are further problems. Like if there are more pipeline stages, that means that there are more instructions with possible issues between them, which might require more circuitry for hazard resolution, forwarding, etc. And this forwarding circuitry typically adds muxes to the data path, right? And that will further increase the combinational path. So assuming that after splitting 1000 into 5 equal pieces, you get 200 each, is already not a good assumption. It will be more than 200 because you need to account for that extra muxes for forwarding, etc. So you see, you have diminishing returns with each additional pipeline stage that you add, right? So if I could plot the number of pipeline stages, here, and the achievable clock frequency, it will look kind of like this. Initially, there will be a pretty fast increase. Like for example, when you convert single cycle into a 2-stage pipeline, the incremental improvement in performance is quite high, but then it will sort of taper off. And at some point, after like 15 pipeline stages, it becomes extremely incremental. So very, very minute improvement for every stage. So yeah, so that answers the question. Basically, you cannot arbitrarily keep increasing it. You can arbitrarily increase, but the returns diminish to the extent that at some point or after a point, it becomes very, very negligible. The improvement in performance you get is very negligible. Sorry. Next one, the following code is run on a 5-stage pipeline ARM processor. Write down the possible hazards assuming that it is a single issue processor. What if it is a single cycle processor? No hazards at all anyway, right? Hazards come in only when you have pipelines. So if it is a single issue processor and if it is an out of order superscalar processor. What if it is a single issue processor? The only type of hazards that you need to worry about other than control hazards, and obviously there are no control hazards here, only data hazards, because there are no instructions that change your program counter abruptly, right? So you need to worry only about data hazards here, and the only data hazard that is present is in a single issue processor. Row hazard or true data dependency. So for example, here you have R3 being written by an instruction and here R3 being read by this instruction. So it's a true data dependency where this reading should happen only after this writing, right? And if these two are back to back, this writing happens only in the write back stage, whereas this reading happens in decode stage. So by the time this reading happens, writing wouldn't have happened, right? And that's your row hazard. The attempt to read before writing. So we have to ensure that write happens and then read. So read after you write. So any violation of it or a potential violation of it is a row hazard. So where are the row hazards here? There are quite a few, as you can see. So do we have a row hazard here? Yes, right? So you are writing to R2 and then reading R2. For store instruction, R2 is an input. So yes, there is a row hazard here. It's actually a memory to memory copy issue, but nevertheless, it's a row hazard. And then we have here, and where else? Is it the same here? Not really, because this R3 is from this R3. And that's all, right? So we have an issue here, we have another one here, another one here. So 3 of them. Anything else? All right. Yeah. So those are the hazards that exist in a single issue processor. How about for an out of order superscalar processor? Will those issues that existed earlier still exist in this case? Row hazard? Yes, row hazards can never be eliminated, right? Its effect can only be mitigated by forwarding. That is any performance penalty. It's not something that you avoid altogether. It's something that you deal with rather than avoid. Because it represents a flow of information, so it's not something that you try to avoid. So all the issues that existed earlier now still exist, even in a superscalar processor. Even in a superscalar processor, there is absolutely no way instruction 5 can execute ahead of instruction 4. Because instruction 5 requires the data that is created by instruction 4. So that order cannot be changed, no matter what you do. right? Because the data is simply not available for the second, that is instruction 5 to run. But there are other issues as well. What are the other issues? Now that order can be changed, we need to be mindful of two other hazards, which are var and var. Var is called anti-dependency and var is output dependency. What are the cases of anti-dependency here? Let me just remove the true dependency for now. What are the cases of anti-dependency? We have here and also here. Is that all? Anti-dependency associated with R3? R3 of instruction 6 has an anti-dependency with any others? Well, all the way here as well. These two. Because there is a potential that the superscalar processor could arrange instruction 6 ahead of instruction 1. As long as it's within the window that the superscalar processor looks at. You know, superscalar processor always looks at a certain window for rearrangement, right? So as long as it's within the window, there is a potential that the two instruction could be considered for rearrangement. And then you need to be worried about dependencies, anti-dependencies here. So for example, if instruction 6 is put ahead of instruction 1 and 2, there are issues, right? Because instruction 1 and 2 will end up using the value of R3 written by instruction 6. So yeah, these are all anti-dependencies. So we have it here, we have it here, we have it here, and we have it even here, these two. So yeah, we have issues. Anything else? There is anti-dependency between this and this. Here, these two with this, and even these two with this. This is something that we don't really end up worrying about though, because there is a row hazard. So if this instruction 4 cannot go ahead of instruction 3, right? So there is no possibility of these two. So this alone, getting ahead and causing issue here. But yeah, it's still something which still falls within the category of anti-dependency. So yeah. How about output dependency? What is the problem with anti-dependency though? If let's say instruction 6 gets ahead of instruction 5, instruction 5 could end up using the value of R3 returned by instruction 6, which is not how it should be, right? The value of R3 here is supposed to be the value of R3 from here, created by sub-instruction, which is instruction 4, not by the sub-instruction, which is instruction 6. So yeah, that is anti-dependency, and here you have output dependency. So if instruction 6 gets ahead of instruction 4, or conversely instruction 4 is executed after instruction 6, the value of R3 at this point will be the value of R3 returned by instruction 4, not by instruction 6. So the instructions that follow it will end up using the value of R3 from instruction 4. And that's not Okay, right? So this is output dependency. Now, how can you deal with these hazards? By the way, output dependency is called wow, write after write, because this write of R3 by instruction 6 should happen after this write of R3 by instruction 4. So that's write after write hazard. By the way, all these dependencies do come into play even at a macroscopic level. Right now we are talking about stuff at a register level, right? But it happens in all scenarios where multiple parties could end up reading and writing from the same location. And if there is a need to maintain some kind of sequentiality, then there are these hazards. So yeah, what can you do about these hazards? Let's first look at these two hazards. Row hazards have only one way they can be dealt with, which is by forwarding data or by introducing gap between the two instructions such that the hazard doesn't exist anymore. So it's possible that the superscalar processor can rearrange instructions in such a way that these two instructions may not be running back to back. Okay, so the superscalar processor can insert other filler instructions in between, which will eliminate the hazard altogether. Or if it can't be done, you can do forwarding. So that's a way to deal with row hazard, and that's the only way to deal with row hazard. Either rearrangement or forwarding, or stalling, worst case. Okay, if nothing works, we have to make sure that this instruction is stalled so that this instruction gets past a point whereby the data is available to be forwarded to this instruction. No other workaround for row hazards. But how about for var and wow? Var and wow manifest only because of our attempt to reuse registers which are no longer required. For example, here, after the store and load instruction, the value of R3 is no longer required. R3 contains an address, and we use the address to do a memory to memory copy. And we don't need that address anymore, at least not in the near future. And since registers are precious real estate, the moment it becomes free, you will use it for something else. And here we use it to store the result of addition of R2 and R1. And now you have your result here, which has absolutely nothing to do with the value that was held in R3 earlier. No connection at all. You are just putting a new fresh value into R3. Right? So there is no real correspondence between the two. So physically they could be in two separate registers. But the programmer cannot explicitly mention it at the time of programming because the registers visible to the programmer is limited. And any attempt to increase the number of registers visible to the programmer will increase the instruction length. Because to identify one among more possible registers, you require more bits. And that is essentially changing the instruction set altogether. You have to recompile every single code out there. Got it? So that's not very practical, and that's why the renaming or the allocation is done by the hardware at runtime in superscalar processors. So a superscalar processor which is capable of register renaming by the way, though theoretically it is possible for a superscalar processor which can do out of order processing to be incapable of register renaming, in practice almost every superscalar out of order processor can do register renaming, because making it an out of order processor without being able to do register renaming, doesn't really give much performance improvement. So practically every out of order processor can do some level of register renaming. So here this will be R3A and this will be some other R3, R3B. So what happens in this case is there will be a large pool of registers, several tens or even hundreds of registers. You make any or take any register that is available and just label it as R3A and then use it. And now that there is a new R3 required, take another register, let's say this one, and attach a tag R3B. And this tag will be automatically attached or inserted by the hardware in a processor that is capable of runtime register renaming. How about here? Is it a new R3 or the same R3 in the previous instruction? It's the same R3. If it is a true data dependency, then it is actually corresponding to the same thing. So this is the same thing as this. How about this R3? This is a new fresh R3 because this value is subtracted from this value and the result of that goes into R3. So this R3 does not refer to the same value as this R3. So this is actually a new copy of R3. And then here it is the same R3 because it's a true dependency. And this R3 is a totally different R3, so it's a new R3, R3B. And now you see there is absolutely nothing stopping this instruction from getting ahead of all these. An out of order processor can rearrange and execute this ahead, thereby reducing the waiting time and improving or enhancing the performance. Got it? So that's a register renaming that is required for R3. Is there anything else that is required? Any other anti or output dependency? No. Now coming back to true data dependencies. Oh, by the way, when the processor does this register renaming, at some point when this instruction is committed, this instruction will be committed and instructions will be marked as committed or retired in the same order as program execution. So the instructions are fetched and issued in the correct sequence in the program order. Committing is also done in the program order, so that if there is an exception, then the exception created by those instructions which were rearranged or gotten ahead of other instructions won't be. Like for example, if there is an exception in the LDR process, which could happen because of a wrong address being sent to the memory, then this instruction should not commit its result, right? Basically, R3D should not be committed, should not be considered to be a new R3. So in order to prevent these kind of issues, you commit the results only in the same program order, same order as the original program. But in between, that is the exact execution, like for example, addition of R5 and R6 and storing the result in R3D can be done anytime. It doesn't have to follow the program order. This instruction does not have to wait for these instructions to complete before it can add R5 and R6. So once this instruction is committed, R3A will be released back to the pool. So once this is marked as committed, because now the value of R3 is superseded. R3 that this instruction's hard is superseded, right? So now at the point when this is committed, R3A will be marked as deleted. So now this R3A could potentially be used for something else. It could be R5C or R6D, whatever. Okay, so the correspondence between real physical registers and the logical registers that are mentioned by the program is a correspondence that is maintained in some sort of a table or tagged by the superscalar processor, out of order superscalar processor. Okay, so it's not a one-to-one correspondence anymore. It's not even a fixed correspondence. It's dynamically allocated and reallocated by the hardware at runtime. Okay, now coming back to the row hazards. What are the various row hazards here? You have one here, and how will it be mitigated? This is a memory to memory copy scenario where you can it's a memory to memory copy scenario where you could forward the data from the W register to the M stage. So W to M forwarding can mitigate that scenario. But having said that, this will come into play only when it will not introduce a stall, because strictly speaking, this is a scenario where you have a load instruction followed by an instruction which makes use of the data that is written by the load instruction. So it is in some sense a load and use scenario, which will cause a stall to be inserted if we follow this expression. Because this expression does not really care about whether the instruction that follows a load is a store. This is applicable for load and use, which includes a load followed by a store. So you should add an appropriate exception condition. So here you should add an exception condition which deals with the memory to memory copy case. So if it is a memory to memory copy case, then this should be zeroed out. So it should be something like and not of memory to memory copy case. Then you introduce a stop. So by adding that appropriate exception condition, and only by adding that exception condition will this become relevant actually. Otherwise you will have one stall anyway. But bear in mind, there is no exception condition possible if it was R2 here. Then one stall is inevitable. Because then it is a load and use case. It will not be considered a memory to memory copy scenario. It will be a memory to memory copy scenario only when it is a data source of the store instruction, not if it is a base register. Because data source is available only in memory stage, whereas the base register is required in execute stage. So if this is in execute stage, and since this is created only when load instruction reaches the W stage, or only at the time when load instruction transitions to the W stage, we don't have the data by the time we need it. So if this is R2, a store is inevitable. But if this is not R2, and if R2 happens to be the data source of the store instruction, then we can afford to wait for one more cycle. So it's okay for the load instruction to reach W stage and the following instruction to reach M stage. Then the data is available at some point when you need it. So that completes that. Then these are all standard forwarding cases. What is this forwarding? It is M to E forwarding, because this will be in M stage by the time this needs the data in E stage. This will also be an M to E stage forwarding. This will be in E stage when it needs the data, and this instruction will be in M stage and would have created the data. So you take it from M stage or M register to E stage. And that's it. And here is a scenario where you will have matches with, so here when you look at the equation for forwarding, that match 1 W to E and match 1 M to E will both be true. Match 1 because it's a first register. Here it will be match 2. And this will be true and this will also be true. And when there is a match with WE as well as M to E, you will be giving priority to M to E because that's a more recent data. Right? Yeah. So in this case, there will be both matches, but this expression that we use for forwarding will ensure that WE match will be considered only if ME or EM match is not there or is not true. So yeah, that completes that. Yeah. Now, match the following. It's quite easy by now. Anti-dependencies. It's var. True data dependencies is row. And output dependencies is var. Anti-dependencies and output dependencies can be resolved by register rename. And true data dependencies can mostly be resolved by forwarding. I have this mostly here because forwarding alone can't help with scenarios like load and use. You need to have a stall plus forwarding to deal with it. But in all other scenarios, you can resolve it by simply forwarding. When this was asked in the question, in the exam, some smart people wrote, by waiting or stalling, and here also by stalling, which is technically correct, but practically useless answer. Because any issue can be eliminated by waiting. Our attempt to not wait and waste time is what leads to all these hazards in the first place. Right? That reminded me of this joke that people say about Microsoft, right? Heard of the joke before? That there was a helicopter which was a bit lost and wanted to land in Seattle airport, and they saw a tall building and a bunch of people there and shouted out, "Where are we?" And it was Microsoft building, and they shouted back, "You are in a helicopter." So yeah, this answer is kind of similar. Technically correct, but practically useless. Okay, so yeah, anyway, we will stop here for now, and we will continue the rest